Hey everyone, and welcome back to AI Podcast. We're diving deeper into AI voice synthesis today, part 3 of our 10-part series. It's getting pretty wild from here on out.
Remember back when we started and we were talking about those robotic TTS systems? The ones that basically, well, they sounded like robots.
Yeah. We've definitely come a long way from those early days of concatenative synthesis, just piecing together those pre-recorded bits. It's crazy how far we've come in actually creating synthetic voices that sound natural. So like think about those old GPS voices or like those automated phone systems. They couldn't like capture the natural flow of human speech at all.
So true. And remember formant synthesis, trying to actually recreate the whole physical process of speech, but, it still just didn't quite get there. But then deep learning came in and neural networks, and they completely revolutionized the whole game. Yeah, total paradigm shift. Neural networks are able to look at, these massive amounts of data, human speech data, and they're picking up patterns, subtleties, things that the older methods couldn't even, dream of. Like, they're learning the code of human language, from the individual sounds to, rhythm and intonation and all those things that make us sound human.
And that brings us to what we're talking about today, two absolutely groundbreaking models, WaveNet and Tacotron. They really, push the boundaries, how human-like AI voices could sound. But what's so cool is they each took a totally different path to get there.
Yeah, it is fascinating how these two innovative approaches kind of emerged, almost at the same time. So WaveNet, it was developed by DeepMind, and it really focuses on just generating sound waves, like sample by sample. It's like building a house, brick by brick. WaveNet is like super carefully crafting every single sound.
Okay, that sounds good. Incredibly detailed. But how does it work, technically?
So WaveNet actually uses convolutional neural networks, or CNNs. And, CNNs, they're usually used for visual data, like for analyzing images, because they're really good at, understanding information in grids. But here's the cool part. WaveNet uses what's called dilated convolution layers. These layers actually allow it to analyze the audio over different time scales, so it can, capture long-range dependencies in speech, that creates the natural flow.
So it's not just looking at the sounds on their own, but how they all fit together in a sentence. We don't just say words one by one, but we kind of create this whole melody with our voices.
Yeah. It's really being able to kind of grasp those long-range dependencies, that allows WaveNet to generate audio with such remarkable detail. Think about all those little things, the breathiness, the tiny little variations in pitch, and even the emotional tone that we convey. WaveNet can pick up on all of that.
Wow, incredible. The early TTS systems, they could never even dream of that level of realism. But I'm guessing this level of detail has to come at a cost, right? Analyzing sound at that level has to be super computationally intensive.
Yeah, for sure. That's the main drawback of WaveNet. It needs a lot of computational power.
Yeah.
Which, at first it made it hard to use for real-time applications. Imagine trying to have a conversation with a virtual assistant that takes forever to process each word. Not really that practical.
Yeah, definitely not. So that's where Tacotron steps in, right?
Yeah.
You mentioned it takes a totally different approach.
Exactly, yeah. Tacotron was also developed by Google, and it tackles the problem from a whole different angle. So instead of generating the audio directly, Tacotron focuses on creating what are called spectrograms.
Spectrograms. Okay,
Yeah.
so those are visual representations of sound frequencies, right?
Yeah.
Almost like a fingerprint of a sound.
Yeah, you got it. So Tacotron, it takes text as input, and then it transforms that into a spectrogram. And then the spectrogram can be converted into audio by using a separate algorithm called a vocoder. So it's kind of like creating a blueprint for the sound, and then you have a builder, actually constructing it from that blueprint.
Okay, that's fascinating. So how does Tacotron actually manage to convert text into these spectrograms? I'm imagining there's some serious neural network magic going on there too.
Oh, definitely. So Tacotron, it uses what's called an encoder-decoder structure, and it's based on recurrent neural networks, or RNNs. RNNs are really good at processing sequential data, like text, because they have a memory, which lets them understand how, the previous words in a sentence impact the ones that come after.
Yeah.
And just like WaveNet, Tacotron uses attention mechanisms.
Attention mechanisms. We talked about those before for other AI stuff. It basically helps the network focus on the most important parts of the input, right? Like how when we read, our eyes don't just scan across all the words evenly,
Yeah.
But we kind of zero in on the key phrases and ideas.
Yeah, that's a good way to put it. So for Tacotron, the attention mechanism basically helps align the input text with the output spectrogram. It's making sure that the intonation and the emphasis is spot on.
So Tacotron streamlines things by focusing on the spectrograms first and then converting those to audio. So what are the advantages of that?
Well, one of the biggest advantages is that Tacotron is way easier to train than WaveNet. It doesn't need as much data or computational power, which makes it, way more practical for real-world stuff. And it's also more adaptable to different languages and accents because it's not like as tied to the really specific acoustic characteristics of a particular language. You can think of it like this Tacotron is learning the grammar of speech, the underlying structure that's common to all languages, whereas WaveNet is more focused on the pronunciation and nuances of a particular language.
That makes sense. But I imagine Tacotron probably has some limitations too, right? I mean, every system has weaknesses.
Oh, for sure. Tacotron isn't perfect. It's really good at capturing the flow and intonation of speech, but sometimes it can stumble on finer details, like pronouncing unusual words or those really complex sentence structures. And even though it's more efficient than WaveNet, it still needs powerful hardware to run well.
So both WaveNet and Tacotron, they kind of bring their own strengths and weaknesses to the table. WaveNet generates crazy realistic audio, but it's computationally demanding. And Tacotron, it's more efficient and adaptable, but sometimes it kind of misses those finer points. So they each offer something unique.
Exactly. And this leads us to the next chapter in TTS, Tacotron 2.
Tacotron 2. Okay, this is where things get really interesting, right? So is this where the two approaches, WaveNet and Tacotron, finally meet?
You got it. Tacotron 2 cleverly combines the best of both worlds. So it uses Tacotron to generate the spectrogram, laying out the structure, the intonation, and then it feeds that spectrogram into WaveNet, which then produces, the final high-fidelity audio. Think of it like having an architect design the blueprint and then a team of really skilled craftspeople meticulously bring it to life.
Wow, that sounds like a pretty killer combination.
Yeah.
So would you say that Tacotron 2 basically solved the limitations of the previous models?
Yeah, to a large extent, yeah. It managed to get that remarkable quality and efficiency. And, it kind of paved the way for a way wider adoption of AI voices across a bunch of different applications.
Okay, so before we go into specifics, let's do a quick recap of what we've talked about so far. We started with the limitations of, those early TTS systems, and then we moved on to the revolutionary deep learning models, WaveNet, which focuses on generating audio directly, and Tacotron, with its very clever approach of creating spectrograms. And finally, we get to Tacotron 2, which very beautifully combines the strengths of both.
That's a good summary. So those who are interested in hearing more, stick around. And, those who are happy with the highlights can move on to something else. But now let's, dive deeper into all these fascinating details of these models.
Okay, let's unpack this. Imagine a sound wave.
Imagine a sound wave, right? It's basically a bunch of peaks and valleys, representing those tiny little changes in air pressure over time. And a typical convolutional neural network, it would analyze, this wave in these, small chunks. It'd be like sliding a magnifying glass along it. But this is where dilated convolution comes in. It's pretty brilliant.
Okay, so this is where I get a little lost in the technical stuff. Break it down for me. What makes dilated convolution different?
Okay, think of it this way. So dilated convolution, what it does is it expands, the view of those convolutional filters. So instead of looking at consecutive samples, it kind of skips over some strategically. So it widens, its perspective on that sound wave. It's I guess you could say, using a wider magnifying glass that can see not only those fine details, but also those broader patterns, within the wave.
So it's like seeing the forest and the trees at the same time, getting the small details, but also the overall structure.
You got it. So it's this ability to grasp those long-range dependencies, that allow WaveNet to generate such natural-sounding audio. It learns how those sounds influence each other, even over pretty long periods of time. When we speak, our sounds aren't isolated, So, for example, the way we pronounce a vowel, it can be affected by the consonants that are around it, and even by the overall rhythm of the whole sentence. And WaveNet, it can capture these really complex relationships.
Wow, that's amazing. It's learning the the grammar of sound. It figures out those unspoken rules of how all the sounds actually work together to create meaningful speech.
It is pretty amazing, and because WaveNet is working directly with with that raw audio waveform, it captures a crazy level of detail. It's like having a really high resolution photo of the sound. It reveals all those tiny nuances that those earlier methods just couldn't get.
But wait, didn't we say that WaveNet's biggest drawback was that it was, computationally expensive? So if it's analyzing audio at such a granular level, how could it even be practical, for things like virtual assistants or voiceover software?
Yeah.
I mean, wouldn't it take, like, forever to generate even, a short sentence?
You're right, that is a valid concern. And it's why WaveNet, like in its original form, wasn't really that suitable for like real-time stuff,
Yeah.
generating audio like sample by sample, where, each sample depends on all the ones before it. Yeah, it's a super time-consuming process. But there have been some major like advancements since then. Remember those other vocoders I mentioned? Parallel waveGAN and
Oh,
MALGAN.
those were the ones that, like, they offered faster synthesis without sacrificing too much quality, right?
Right. So these newer vocoders, they use different techniques, often based on generative adversarial networks, GANs, to produce high quality audio way more efficiently. They're kind of like, shortcuts that let us get like similar results to WaveNet, but without that massive computational overhead.
So it's like having a team of, like, incredibly efficient builders who can construct the same masterpiece, but way faster.
Perfect analogy. And this is why, WaveNet's impact has gone way beyond just its own capabilities. It like set a new standard,
Hmm.
for audio quality. And it inspired like this wave of innovation in vocoder technology, which made it possible to, integrate those realistic AI voices into like so many different applications.
Okay, so WaveNet really revolutionized how we generate audio. Now, I'm curious about Tacotron. It goes in a totally different direction. It works with spectrograms instead of the raw audio. So, like, what's the advantage of that?
Well, you can think of spectrograms as like a more abstract representation of sound, so instead of dealing with those raw like fluctuations in air pressure, Tacotron's working with like this visual representation of how those fluctuations are like distributed across different frequencies over time. It's like looking at like a musical score instead of listening to like actual performance.
So it's like capturing the essence of the sound, like the melody, the rhythm, without getting, bogged down in the specifics of every single note.
Yes. And this abstraction, allows Talkatron to be way more efficient and adaptable. Remember how we talked about how WaveNet needs to learn like the very specific pronunciation nuances of each language? Talkatron, though, can learn those broader patterns of speech that are, common across languages. It's like learning the grammar of music, the underlying principles of harmony and melody that apply to all the different genres rather than like memorizing the specific notes of each individual song.
That's a really good way to put it. So Tacotron is more about understanding, like, the fundamental structure of speech, while WaveNet is more about recreating those fine details, the sonic ones. They each have their strengths. And it seems like they complement each other perfectly in Tacotron, too.
Absolutely. So let's dive into how Talkatron actually works, As we said, it uses an encoder-decoder architecture based on recurrent neural networks, RNNs.
Okay, remind me how those work again. They're the ones with the memory, right?
Right. So RNNs are designed for processing, sequential data like text or like time series, where the order of the elements is like super important. They have those like internal loops that allow them to retain information from previous steps, which makes them perfect for like natural language processing and, obviously speech synthesis.
So how does that apply to Tacotron? How does it take text and turn it into a spectrogram?
Okay, so think of the text as like a string of beads, and each bead represents a word. So the encoder in Tacotron, it takes this string of beads and kind of like threads them through its memory, creating this compressed representation of the entire sentence. And that representation captures, not just those individual words, but also like the relationships between them, the meaning, the intent behind the sentence.
It's like it's reading the sentence and then summarizing it.
Yeah, that's a good way to think about it. So then, this summary, this compressed representation of the sentence, it gets passed on to the decoder. And the decoder's job is to, like, unravel this summary and transform it into that spectrogram.
And how does it do that? I'm guessing this is where those attention mechanisms come back into play.
Exactly. So just like WaveNet, Tacotron uses attention mechanisms to make sure that that output spectrogram, aligns perfectly with the input text. It's like the decoder is like paying very close attention to that summary,
Right.
making sure the emphasis and the intonation of the speech like matches the meaning and the intention of the text.
It's incredible how these neural networks can kind of, like, mimic how we process language and sound. It's almost like they're developing their own, understanding of what they're working with.
That's what makes this whole field so captivating, We're essentially teaching machines to like communicate like we do, to understand the subtleties of human speech and then recreate them, with this
Mhm.
crazy accuracy. As these models get better and better, I mean, who knows how sophisticated and natural sounding AI voices will become?
Yeah, this has been amazing so far. We've gone from those like clunky robotic voices from the past to these crazy complex systems like WaveNet and Tacotron, really pushing the limits of what's possible in speech synthesis.
And this is really just the beginning. There is so much more to uncover in this field,
You're
just
right.
for a voice.
That's a great way to put it. And then Tacotron 2 comes in and like that blueprint comes to life in this like really amazing way.
Right. Tacotron 2, it takes that spectrogram that, Tacotron generated and feeds it to WaveNet. So it's this like really powerful combo of the two.
Tacotron 2 is really where it all comes together, right? I mean, Tacotron lays out that high-level structure, the melody, the rhythm, and then WaveNet comes in and adds in those super important details, the ones that make it sound, like a human voice.
It's like a composer making a symphony. And then you've got this like world-class orchestra bringing it to life with all those, harmonies and dynamics.
Perfect comparison. And the results are really, like, mind-blowing. Tacotron 2 can, like, make speech that's basically indistinguishable from a real human recording. And it's not just the words, it's like the emotion, those little inflections, even like the breathiness of a voice.
It's really like crazy how far we've come in such a short time, from those like robotic sounding systems to AI voices that can almost fool you. It's really amazing what deep learning can do. And the researchers, who are pushing the boundaries of what's possible.
It really is. And it's not just like about creating realistic voices. It's about opening up all these possibilities for communication, for accessibility, and like creative expression.
Imagine a world where anyone can have their own like personalized AI voice, where, language barriers are almost non-existent, where books can be narrated by, the authors themselves, where we could even hear historical figures like actually speak to us.
The possibilities are like endless.
They really are. So as we wrap up this episode, I want to leave everyone with a question to think about.
Okay, what is it?
What does it mean to be human? In a world where machines can speak in our voices, where that line is getting blurrier between human and artificial.
That's a deep one.
It is something we'll keep, exploring as this technology keeps advancing. But one thing is for sure, the journey of AI voice synthesis is far from over, and it's going to be one wild ride.
We are definitely here for it. And thank you all for joining us on this, incredible deep dive into the world of AI voice synthesis. We hope you enjoyed it.
Yes, thank you for listening.